Alrighty, so I think the next one is check 4, problem 10. Check subtree. Okay, so CHO4P10 check subtree.ch. Our templates, go to our templates, copy out our template. Put this here. Here we go. Yep. And convert this to check subtree. I've already read the description, so I put another T1 and a T2. And that will take... Okay. And so it might say something like, is this a subtree of this? Well, no, it's not. Let's do it with our vectors. I like the vectors better. Is this a subtree of this? The answer should be true. Well, let's do the easiest one. Is this I guess is this a subtree of this? The answer should be false. What about, is this a subtree of this? And the answer should be true. Okay. Actually, when I said that, I meant to say, is this a subtree of this? The answer should be true. Similarly, is this a subtree of this? The answer should be true. Okay. Alright, so what is the problem? Check subtree. T1 and T2 are two very large binary trees, with T1 much bigger than T2. Create an algorithm to determine if T2 is a subtree of T1. A tree T2 is a subtree of T1 if there exists a node n in T1 such that the subtree of n is identical to T2. A tree T2 is a subtree of T1 if there exists a node n in T1 such that the subtree of n is identical to T2. That is, if you cut off the tree at node n, the two trees would be identical. Now they're using the word identical, and I don't know whether they mean literally identical as in the same reference in memory, or identical as in the same value. The two trees are identical in the sense that they are equal, they're the same tree, but maybe not actually the same data, just a second, let me get some music started for myself. Alright, I need to plug in my phone. So, identical is slightly easier. Identical is in reference equality. It's slightly easier than identical as an equality immutable in all languages, right? But I don't think I read it as identical being referent equality. I think I'm read it as identical as being value equality. And for that reason, well, actually, in a language like Clojure, it really doesn't matter, right? I mean, identical is identical, and it's something I never thought of. But anyway, identical is identical, and I don't know what I was saying. Equality is easy, right? On a reference language, like basically if I didn't have reference equality in a mutable language, or in a language with mutable data structures, then I would need to not only, when I detect what appears to be equality between two nodes, I would then need to compare all children nodes as well, right? Because if I can't do reference equality, the only thing I can do is actually compare them piecewise, each node, and say, yes, they are equal. But in a language like Clojure, you can't just do equality on the two data structures, the two immutable data structures, and they will only be equal if they are literally equal. Now, if you have reference equality, right, identical, if that's what identical means, is reference equality, then for either one, right, for either closure or for either mutable or immutable languages, you can just do reference equality on the actual nodes, right? And but I mean, it doesn't really make a huge difference in terms of the implementation in an immutable language, whether we're talking about reference equality or value equality, or at least not in this language. But if this were a mutable language or a language with mutable data structures, doing value equality is more complicated, right? Because you have to actually recursively descend the entire data structure and check that it's equal, as opposed to this language or closure where you can just do value to value. Another sort of interesting thing, as I understand it, is that closure actually is effectively calculating hashes all the time as you're doing equality, and there's an equality hash. What you're actually comparing isn't actually the data structure itself, but the hash of the data structure. And for that reason, the first time you compare a data structure, it has some cost to it, but the subsequent times after that, as I understand it, it's basically free, right? Because the data structure has already had its hash computed, and so it doesn't need to recompute the hash, because knowing it's an immutable data structure, and so it just actually, it costs nothing to really compare that to something else, or it only costs the something else. It doesn't cost the thing you've already done the equality check on once, as I understand. But I haven't actually ever looked that up. I think I just heard it. So, anyway, check subtree. So we got T2 and T1. T1 they're both very big graphs, evidently, which I don't think really matters for us. Well, I mean, at least not for T2, right? It doesn't matter how big T2 is, because we're just going to do equality on it, T1 kind of matters. And T1 does matter. In fact, given what I just said, there could be a performance problem with this. Okay, let's think about what is the minimum complexity. Oops, sorry, I gotta pause for just a minute. Yeah, thinking about this a little bit more, what is the minimum complexity this algorithm could have, right? I feel like it's at minimum linear, to where linear is the total number of nodes in the graph, right? Right, I mean, I can't do equality on two things. Like, there's no structure to this graph that lets me. It's just a binary tree. There's no structure to it. So I have to basically look at every node. Now, I think we can maybe look at slightly less than all the nodes, but conceptually, I just need to look at every node and ask, is T2 a subset of T1? So let's just first write the just dumb brute force, no cleverness solution at all, right? And I'm going to copy this from chapter 4 problem. Nope, I wrote that one myself, didn't I? Chapter 04, problem 08. Yeah, I think this is a better name. So this is our good old data structure for our vector, where it's like, it's either got zero children, 1 child, or 2 children, right? Left or right. So this is the value, this is your left, this is your right. And this thing basically encompasses that. So first thing we need to do is just convert both of them to from nodes into locks, basically. So let's say L1 and L2, just map node to lock on T1 and T2, right? And having done that, we now have locks. What sort of questions do we need to ask? Well, realistically, all we need to do, I believe. Actually, I don't even know if we really need L2 as a whatever. I mean, like, I think all we should need to do is basically just. Well, let's minimize that then. Okay. We're going to take T1, right? We're going to create a. We're going to convert it into a lock, right? By making it by wrapping it in zipper. We're changing T1 from a node into a location, basically. You know, a zipper, if you will. And then all we're going to do is basically just say iterate zip/next, right? Which will first return the root, but then we'll return every single element. And because we know we started at the root right here, we can just take while zip/end, right? So we're going to go all the way from the first node all the way through the entire tree to the last node, right? And let's see. And if the trees, you know, and what are we basically asking? We're basically asking, is it ever the case that that this guy, his zip/node, is equal to this guy, right? That's, I think, what we're asking. And if that is the case, you know, and I guess we're asking, is that empty, you know? And if it's empty, that means that T2 does not occur in T1. But if it's not empty, then, you know, I don't know how empty works. I think we checked, and empty is actually takes the first of the seek. Right, let's see. Empty takes the first of the seek, I think. Yep. Or takes a seek and takes the not of. Oh, okay, yeah. Well, that's another way of doing it. All right. So checks if it's empty. So I'm pretty sure this, you know, it's a constant time cost operation. Well, anyway. And it's, we're just going to take the not of that, right? Because we want to reverse it. We want to make it so that if it's not empty, that means we are a subtree, because we have at least one node. This node shows up at least one time in here, right? If we are empty, that means we are not a subtree. So let's see what we get. Could not resolve symbol zipper. Oh, good call. Yeah. Let's go back here, pull this in. Don't know how to create IC from blah blah blah. T1, T2. What's going on here? Empty question mark. Oh, we are doing a thread first, not a thread last. Alright, so they're always false, unfortunately. Let's see what we actually get. We always got the empty. Okay, so that's the issue. Let's back that up a bit and just see all the things we actually get as zip/next. That's weird. We got the lock, right? We took T1. We converted it into a location. We then iterated on zip/next. That should be returning at least the initial thing, right? Why is that not doing that? Oh, I did it again. I do it every single time. It's the complement of zip.end. Okay. Are we getting a vestigial? No, this is just the lock itself. Alright, so this is saying I had nowhere to walk, basically. And that's pretty much the problem, actually, but I'm going to assume there must be more to it, because that's pretty easy, right? So, I think, what could we do? Well, we are technically walking through every single node in this tree, right? In T1, which is a bit expensive. Now, let's think about that. Is that reasonable? Well, I can't see how you could possibly be going. I can't see how you could possibly be doing better. Let's pretend that let's do the weirdest case, right? Which is where this tree, and just to make it, I think, easier to think about, right? Where the T1 is gigantic, right? I mean, billion element tree, right? And the T2 is just a tree with one node in it, right? So that's I think the worst, what do they call that? Dimorphism? It's like, how elephant seals are like, the males are like 5 times bigger than the females. What do you call that? Dimorphism? Yeah, it is a word. Okay. What does dimorphism itself mean? Such as... Oh, so dimorphism is... Oh. Is dimorphism... Alright, anyway, whatever. Thought I'd use a new word and it doesn't look like I succeeded. Alright, so one is huge and one is tiny, right? As big as it can be and as small as it can... Well, not as big, but really, really big and as small as it can be, right? If that's the case, is there any reasonable thing to do other than scan every node? Well, yes. Okay, I see something, right? If the smallest one was 1 and the biggest one was, let's say, depth 10, right? You actually know that the tree can only occur at the leaves, right? So first of all, let's go a few things. What if T2 is bigger than T1? That is, it's got a greater depth than T1. And by depth, I mean the deepest depth in your tree, right? What is that? Is this under tree and grass? Okay, so if it's bigger, if T2 has a bigger depth than T1, then you actually know that you can't fit T2 in T1, right? So actually you're just automatically out, right? And now T2 is less than or equal to T1. You know that you can fit T2 in T1. In fact, you know that whatever the height of T2 is, you only need to go that deep on T1, right? And technically, because you know the height of T2, you actually don't need to check the nodes. So let's say T1 is 1, or T2 has a depth of 1, and T1 has a depth of 10, right? You only need to check the leaf nodes for that tree, right? Similarly, if T1 had a depth of 10 and T2 has a depth of 2, you only need to check the nodes. You literally actually only need to check the nodes that are 1 away from leaf nodes, right? That's the only nodes that it could be. So there's actually only, for any tree, you don't need to look any deeper. Or there's basically a line running through the entire tree of all the things you need to check, right? Now, it's not necessarily a flat line, right? If the tree has different shape, it'll sort of follow the shape of the tree, but it'll be a line within the tree that you have to follow. Now, that is the minimum you will need to do. And there's no point, for instance, if you know your tree is of depth 2 and your node is of depth 1, there's actually just no point in checking the depth 1. Sorry, If T1 is depth, yeah, I've already said it. Yeah. So all these things are true. With that said, so it sounds like first of all, like it sounds like the search we want to do is basically a breadth first search, right? We want to start at the root and move kind of downward, right? We don't want to do a depth first search because that's probably going to result. Well, first of all, why don't we? Because we want to spend as much time. Yeah, there's actually a singular line. Sorry, putting thoughts together. There's a singular line through every tree that could be the location. That's an interesting question. How do we figure that out, though, without actually... Like, there's no way looking at a node to know how many children it has. I mean, you can look at how many children it has, but if you do so, then effectively you've already traversed through that child, and so you've already paid the cost associated with it, right? So I don't like. I do see the fact that the ideal path would literally just be walk the line that is the depth of T2 from the bottom, right? In T1, right? Only walk the nodes on that line and check whether each of them matches, right? That would be the ideal thing. But I don't think it's, I mean, like I think we can walk down to that position, right? Efficiently, right? So if I know that I'm, and let's just say I have a perfect tree, right? Right? And so what that really means is that all the nodes, the leaf nodes, are all at the same level, right? And then I have a tree T2 that is a 2-element tree. Let's say, something like this, right? I know that I need to, what I need to do is I need to walk to the, the depth 9 of the tree, right? Which is all the nodes on that tree that are one away from the leaf nodes, right? And I need to be checking all the depth 9 nodes, basically, right? And that's all I need to be checking. I do know that that's true. Okay. But... Okay, so to get to the depth 9 nodes, though, I had to walk through the upper tree, right? So I've already paid the cost of walking across those nodes. So there's really little difference, and I might as well just have visited them too, even though the equality can't exist at that point, right? There's no... But it's only a constant savings, and it's not worth anything. So I might as well just check it recursively. I might as well just check it as I'm descending. It might be worth my time not to descend into the depth 10 nodes if I could write that as an optimization. And I believe I can, right? Because if I know the depth of... I mean, basically, if I know the depth of T2 and I know the depth, and when I say depth, I mean the longest depth of T2, and I know the longest depth of T1, I can just subtract from... Actually, the first check I can do is basically just ask what is the depth of T2 and what is the depth of T1. If the depth of T2 is greater than T1, then it's definitely not going to work, right? And stop. If the depth of T2 is equal to T1, then it is going to work. Or this is at least a possibility, right? And do equality. And if the depth of the 2 is if the depth of T2 is less than T1, then this cannot be a match, but you should check the children. Now that's interesting, because if we do the path, then I'm pretty sure we don't actually need to do equality on the two of them until... We don't need to do equality on either of them until we're actually at the proper depth. That is, we're at the point that T2 and T1 have the same depth. Then we need to start doing equality on them, right? But only then. And so that's interesting, right? Because that means we descended all the way down without doing equality. right? We descended all the way down to the point that T1 and T2 had the same depth, right? Without doing equality. So that was just, well, I mean, like I said, it doesn't really matter because once you've done the equality for T2, T2 is a very cheap thing to do equality on. You're only paying the cost of the equality on T1. And I believe, as I understand it, those have already been calculated. Those are also cheap things. You know, they're sort of, the equality is sort of hidden from you, but it's a sticky thing that once you've calculated it for a data structure, it's still there. And also, I believe, as you modify the data structure, and only the new parts of the data structure do not have equality calculated for them. For all actually I know, it may be the case that equality is calculated as the data structure is built, and so you don't actually need to dynamically calculate equality. It's done, or at runtime calculators. You don't need to. Equality doesn't occur just when you use equality. It may actually occur when you build the data structure in the first place. For all I know, but I believe I've heard that equality is very cheap in Clojure. Amortized wise. So yeah, I mean, like, honestly, if you gave me this problem, I'd say this is the right answer, right? You should definitely do this. This is simple to understand, you know, boom, you're done, you know. But if we want to try to be a little more clever than that, what can we do? We could grab it. Well, I'd like one thing that I've been saying is I'd like a thing that can tell me the depth of a tree. But of course, if I do the depth of a tree, the depth of a tree requires me to literally walk through every node in a tree, right? That's how I get the depth. And so, yeah. So if T1 is truly huge, and T2 is also huge but much smaller than T1, then I can do the depth of both T1 and T2. And if I do that, I don't think I need the depth of T1 though, actually. I think I just need to know, well, I don't need the depth of T1 in the sense that I don't need the total depth of T1. Actually, there's two different types of depths. There's not. There's the depth, which is, really we should call it your height or something. Your tree's height, I guess, right? But I can get the depth in two different, well, the way you get the depth is to say, let's build a function that gives you the depth of a tree. Of T, right? Let's actually say lock. We're dealing with locks now, right? Return the total height of a tree. Wow, height. Maybe that's just not a word, height. Yeah. So I'm just saying that to indicate this is like, I don't know, you might think like zero-based indexing or something. Like it should be, right? So we take the lock. Now this is a bit complicated. The only way I can think to do this is to literally iterate through everything again and do the same thing here. Right? What we're going to do this time is we're going to map on zip slash path, I believe. Yeah. And we're going to take the count of that, right? And then we're just going to say the apply the max of that. And I did it again. And that is your total height of your tree. That is the height of the longest thing in your tree. And let's test that out. I just don't know. TR T expected. And let's do expected is equal to the height of T. And it actually should be a lock, so let's just, for the sake of this guy, convert it into a lock. Oop, okay. And so I'm arguing that this should return 1. Okay. Node lock does take 1 argument. Height takes 1 argument. Expected equality takes 2 arguments. Not call with 1 argument. Where are you getting this? Let's make sure I'm just not, somehow I didn't do something that broke this. Okay, it's definitely this. So 0. Iterate zip next. This is identical code so far. This is the only, oh. Why does it say with 1 argument? Oh, it means the anonymous function cannot be called with 1 argument. That's annoying. I wish it was a little more clear than that. I mean, you know, pointing to the line number would really help, but also... Okay, anyway. Okay, I am not getting what I would expect, and I think that may be because... Let's just see what we got here, actually. I got nil, which is pretty weird. You should definitely get the original lockout. Oh wait, no I didn't get nil, I just keep misreading this. So you got this and nil. Yeah, that's right, okay, so you didn't iterate at all. You took until your nil, which just returned the same node, and so you got the first node and that's it. So now I'm saying, okay, let's get the count. Let's return 0. That's not quite what we wanted, because I think we need to increment that 1 then. Right, okay. And we're going to apply max to that. Cool. Alright, so let's just do a few other sanity checks. How about 0, 1, 2? This should have a total height of 3, right? Gonna resolve symbol blank. Oh. Yep, okay. Let's check slightly more. 0, 1, 2 should only be 2. Alright, okay, that seems pretty good. So we got a thing that gives us the height. And although height does require you to traverse the entire tree, as actually does check subtree as we currently have it written here, right? So really, if you're going to do the check subtree, then don't bother with any of this, right? But we're attempting to do slightly better than this running through every single one cost, right? I really don't think this is a huge... Well, it could become a huge savings if, like, your subtree is height 10, or if T2 is, like, height 10 and T1 is height 14, then that's a huge savings, right? Check subtree is very expensive. It's 2 to the 14th power, right? I think it's actually, I think we read in the book. It said 2 to the k minus 1. I think nodes on our perfect tree, right? And so that's 2 to the 14th minus 1 nodes you got to walk through, as opposed to if you actually have T1 of 14, depth 14, and T2 of depth 10. It's actually just 2 to the 4th minus 1 is what you end up needing to check, right? if you can do this check subtree thing and avoid iterating on things that are less than, or mostly avoid iterating on things that are, you know, on T2s that are less than T1. We're going to have to look at how to do that because I'm not entirely clear how to sort of jump down. Anyway, but we do now have a thing that can give us the height of the smaller one. Since we have the height of the smaller one, of T2, since we have the height of T2, which isn't necessarily the smaller one, we should be able to write check subtree now to be like, okay, you should keep checking things. You know, I'm also not sure. I don't know. I don't know how equality works in the sense that I'm also not sure if equality is lazy in its equality. Like, does it stop doing the equality check the moment two things diverge? So if I have like a vector with 1,000 elements and another vector with 1,000 elements, if they're identical other than the fact that the second element is different on the second vector, you know, will it only really pay the cost of comparing the first element and then the second element? Or maybe the logarithmic of something? Will it basically pay the full cost of having to compare all 1,000 elements, or will it stop doing the comparison the moment the comparison fails? Or at some efficient point at which the comparison fails? I don't know. I don't know, actually, you know. I would kind of hope that it stops the moment the equality fails. And, you know, it does mutably record all the things it had computed the hash of, but it doesn't keep going. I hope I'm not just making that up entirely. Maybe it's a fever dream if that's true, you know. But this check, yeah. I don't know, man. This one's awfully simple, you know. It's kind of hard to argue with this. Now, so just think about it. I'm not too sure where I'm going with this exactly, but we can get the height I have a lot of trouble with that word, don't I? We can get the height of T2, right? And if we have that, what can we do to limit the amount of work we have to do? Well, we can certainly say, hey, if I know T2's height, then I should I don't think we can use zip next. Zip next is just blind. It's just the next depth first search node. But maybe we don't want to use zip next anymore. Maybe we just want to recurse, right? And okay. Let's think about this. Oop. I'm going to say check subtree. I pass in T1, T2. And I'm also going to pass in the height of T2, which we only had to calculate once, you know. And then I'm going to have another guy who's T1, T2, and T2 height, right? And you know, I always like this about Erlang is the fact that I feel like you didn't declare variables that often. Instead, you just wrote all these different like signatures for the way your function would accept arguments, you know, and then it would just basically keep trying from top to bottom. I always pictured like a pachinko machine until it found a match, or you know those babies things where they try to put the star in the star and the circle kind of thing. Until it found a match, and then it would do that one, and then it would often just call into itself a lot of the time. You know, I thought that was a nice metaphor, you know, in terms of thinking about things. But anyway, yeah, we probably want to convert both of them into locks actually too, don't we? So let's just do that for both of them. Well, at least the first one into a lock. So we convert we convert T1 into a lock. We leave T2 alone because we're really done with, we're just going to be doing equality on T2, and we take the height of T2, right? And now that we have the height of T2, we have lock 1, T2, and T2 height. We can say lock 1, we don't need to do this anymore. What do we need to do? Well, now we basically say if lock 1's path, zip/path, count, let's increment it just to include the lock itself, is equal to height, you know, or is equal to T2 height, nope, let's actually just take that as a value. We can also we're going to compare the height to the depth. Okay, all right, whatever. But we can then say things like if it is equal that L1 depth is equal to T2 height, right? If those are the same thing, then this is a point that we should do equality on, right? To return whether it's equal or not. Return whether it is equal that the zip/node of L1 is equal to T2, right? But if L1 depth is less than T2 height, then we just need to recur. So let's actually do that one last. But if T2 height is less than L1 depth, then we're definitely done. And just return nil, maybe. So this is going to return, oh, we got 3 different things returning here. Returning Boolean, I don't like this one at all. We shouldn't do that. This shouldn't even be happening. You shouldn't be going to. So I kind of feel like maybe we should actually. Let's just not go to that place. Let's not need to check. Well, let's need to not. Well, no, we do need to check it because you could pass in a T2 that is literally bigger than a T1. So if that's the case, then I guess you should return false, right? It is impossible that T2 is inside L1 if T2 is taller than L1 is down. This is stupid. Okay, so it is possible for that to be true. This might be true if the two are equal, and this means you gotta recurse. And we don't really need to check it because it's the only possibility that's left. But, and if you recurse, what do we want to do? We just want to go down your left and your right child, right? So it kind of seems like maybe we just want to concat on... This guy's not returning a sequence. He's returning a Boolean, and this guy's also returning a Boolean. Do you want to put him in a map? Maybe. So now they return a sequence of Booleans, ultimately. What does this guy return? He returns the concat of this function. Okay. And L1 writes, if that exists, right? Actually, I don't know whether this will work if this is already nil. And this will return nil if you can't go down. Fine. If and L1 down. Right, so this will return nil if you can go down, if you can't go down, and this will return nil if you couldn't go down, so you definitely can't go right. But then it'll return nil if L1 down was nil, and it'll also return nil if L1 down wasn't nil, but there is no right child. Does that make sense? Do we want to do this, or it feels like maybe we just want to do zip/children of L1, right? This returns a sequence. Okay. And then on those zip-children, we want to map this function to check subtree of the child in T2 and T2 height. Now I think we want to apply the concat. Because now we're returning a sequence of Booleans, and so we just want to return a sequence of Booleans. So now everybody's returning a sequence of, oh, hey, here's our thing where we're gonna, con requires an even number of forms. Okay, doesn't it have it? 1, 2, 3, 4, 5. You didn't put this in there. Okay. So one thing I'm gonna do here is do what I did on the last one. Oh, I commented out at the end. Yeah, I think this is maybe a good idea. Let's just confirm that everything needs to be a, and by that I mean everything in this call needs to always be returning a sequence, and the sequence needs to be such that every item in the sequence is a Boolean, actually. Boolean. Okay. So, okay, cool. So we now know that everybody being returned here is a Boolean, because otherwise that would have blown up. We have a recursive function here. I don't think we need any of this, right? Index out of bounds exception. Zip node of L1 is equal to T2. Okay. Zip node of L1 is equal to T2. That seems reasonable. So basically, I'm just starting from the root, and I'm just going all the way down on to every child of recursing every single time to every child. I'm basically, if the two heights are the same, the usual methodology here is yeah, I guess apply plus, let me think about this, string, apply string, repeat the count of, it's a bit silly, but L1 zip slash path, the count, right? We can take the empty string from that. Okay. And then I don't really need L1 or L2. I guess I do. Let's just print out L1 for now. I'm implying that you're not even getting to that. That's a little hard to believe. Oh, unless this is actually failing it. No. What's going on? End. Why isn't this working at all here? Are we just stuck here? Is this not right? No. Feels like it's just not hitting this at all. Alright. Okay. Okay. Check subtree. Go 2 arguments to 3 argument version. It's not even print lining though, which is what concerns me. Which kind of means probably this is failing. L1 zip path count. Okay, let's just try being really simple here. What? So kind of implying that we're not getting past this point. T2 is not a height, or it's not a log. Damn it. Should I erase all my good work over there? There we go. Three separate lines. Oops. One as a function. I agree. Oops. Okay, so we walked in with the... Oh, what was that? Where does this list thing come from? Where's the list sequence thing coming from? I thought repeat took... Oh. I forgot you gotta apply string this whole thing too, don't you? Okay, there we go. Alright, 0 nil. And it's failing at some point. Oh, the assert failed. Cool. That's what we want. You're saying the thing that was returned here was not a sequence. It would be lovely if you told me what it was, but at least you told me it was not. It is. That looks like a sequence to me. What? That is not a sequence. Okay. I guess I think they're being strict about what sequences really are here. But I guess just maybe that means seekable. No. Sequential, maybe, I mean. Okay. Don't know how to create IST from Java Lang Boolean. You're not complaining about this one, are you? You are. Oh, it's not a. It's just a function of booleans. It's not a function of. But this was for the function of arrays, right? But now we're just saying it's just a function of boolean. Okay, and since we are doing this, we actually don't need this one at all. Okay. It's a flat array of booleans. And I kind of think we're really not using. This isn't right. Right? Sorry, is this the zip children's locks, or is this just the raw children? I think it's the zip children's locks, right? Yeah, okay, so I guess it does work. But I would prefer to get rid of this and say when this works, then similarly when this works, right? Now we can avoid that apply concat thing again. I like that better. This one says check the left tree. This one says check the right tree. Bit of redundancy there, going down on both of them, but that's fine. L1 left says go check the left path. L1 right says check the right path. And we're just going to keep recursing and reconcatenating back together. Now that's fine because everybody returns. Well, now that everybody returns this really, I don't think needs to exist, right? In fact, I don't even. Well, no, this can still occur. This can still occur. Okay. And this will just become nil when you call into this one. And so, like, concat will just remove it. Or it'll become nil at the root level, in which case this guy, we'll just remove it. But I prefer that this guy also return the lock when you find it, right? If you haven't found it, just return nil. Right, so everybody actually has changed their signature from, well, it's not really, no, I guess they haven't, well, no. Now everybody either returns nil if they didn't find it, right? Or if they've decided to short circuit themselves, right? They short circuit themselves when they're literally like, there's no possibility of finding it, right? T2 is taller than L1, right? They check for equality when T2 is equal to L1, you know, and they're like, okay, cool, let's give it a shot, you know? And these are not the same things. The height of T2 is not the same thing as the... I would need to know... Fudge. I'd need to know the height of L1. Wait, do I? That doesn't make sense. I think this whole thing is just not right. Maybe we should have just not done any of this kind of stuff with the height. And instead it's just been like, look, do a breadth first search. I do see one thing we can do. Once we find... If we were to walk through... If we were to walk through all the nodes, right, on T1, knowing the height of T2, right? We could walk through all the nodes. Well, so I say we start walking through the nodes on T1, right? If we were to add the total height for every node at T1 as an attribute of the node, right? We could discard reviewing any nodes where we already know that your parent has a height. Well, no, because we don't know. It could always be the node to the right that we haven't yet explored that actually has the height that is sufficient to make this reasonably work. Coming up on more than an hour on this problem, and I was gonna take a bike ride before it gets too hot today. Yeah, I mean, this is nonsense. This L1 height. These are different heights. This is the L1 height is the. I should have. They actually are. They should be named different things. The L1 height is the depth into the tree you've gone, but your depth is different than your height. You know. I can be a 6-foot tall diver at a depth of 30 feet. Those are different concepts, and you can't just. You would need to take. What we need to do is take the depth minus. So if I'm a 6-foot tall diver at a dive distance, at a total you know, the ocean floor is 30 feet from me, right? Then I know to touch the floor, I need to be at, my head needs to be at 24 feet, right? And that's similar to what we need to be doing here, but that's not what we're doing here. We're actually saying, is the 6-foot tall diver the same height as the depth of his head, you know, which is of the top of his head, which is nonsense. It doesn't mean anything. So we actually need the depth of the ocean minus the height of the diver should be equivalent to the depth of the diver, where the depth of the diver is measured from the point of his head, right? That's when you actually do have the possibility of doing the node equality. But in order to do that, I need to know the depth of the ocean. In order to know the depth of the ocean, I need to basically walk over every element in T2, I believe, in T1, I believe, right? Fudge. If I'm doing that, then I might as well just do this algorithm because I'm already walking over every element in T1. Golly. Golly. I mean, there's, you know, I can take the depth of T1 and the depth of T2 if I want to. It's just, having done that, it's about as expensive as it can get. I've walked through every node in T1 and every node in T2 already. So that's a linear cost, which isn't terrible, but like, what are we even saving on at this point, you know? Yep. Well, I mean, it works for any trees. It does have a linear cost proportional to the size of the larger tree. But I'm not seeing anything. I feel like I need to know the depth in order to prune out large segments of the tree. But if I know the depth, then and how do I, like, all my schemes involve me basically knowing the depth of either the entire tree or every node in the tree, right? Which either are pretty much the same thing, right? We could also do, rather than height being a thing that just returns a number, it could be a thing that goes through every single node and calculates your actual depth by looking at, you know, by basically just looking at the depth of your children and working backwards, right? Right. And maxing for each node, max the depth of all your children, and do that recursively through the entire tree, and boom, you've converted the entire tree to a tree with depth information in it. If you had a tree with depth information in it, then you could fairly easily basically do the same thing, do a breadth first search where you can basically drop all the nodes that that don't have your depth, right, or that aren't as tall as the tree, as T2, right, and only compare on the ones that are T2 and don't recurse on the ones that are greater than T2 at all, right? And that's not hard. But the big thing is the beginning of that sentence where I said you recurse through the entire tree and added this information to every node, right? Now you don't, I guess, technically have to add it to every node. No, you do. You do. You can't know the depth of a tree until you go to the bottom, right? I mean, you can see it in the data structure, but you can't understand it until you actually measure it. So yeah, the only way to know the depth of a tree is to think. The only way to know the depth of any node, the recursive way to know the depth of a node is to ask what is the depth of each of its children and take the max of that, right? You keep doing that recursively. And that recursive definition does require that you hit every single node in the tree. If you've already hit every single node in the tree, there's no point. Like, that's already a linear algorithm. You might as well just do this. Lame. Well, I think that's all I got. And also, I really like it. We are in a heat wave, and it's just crazy. And I need to do some exercise. So I'm gonna go ride a bike. And yeah, that's 410. I mean, it's a solution, right? It works. I feel like it's missing the principal thing, which is what the heck do you do to make this more efficient? I'm kind of wondering whether the well, we'll see. I'll look at this later, and yeah, let's just leave it at that. I'm not even gonna read the hints, but I'll look at this later. Maybe on my own, but still there. All right. Yes, save the file. Okay. Oops, that's not what I meant to do. Extract the file. Commit. Let's do check subtree. I wonder if there's just something, yeah, really obvious I'm missing here. Problem 410. Crack included. Cool. And that's a day, honestly.